Today we're going to be doing something kind of cool. I'm going to show you how to make a bouncy ball fly around the screen like this on an Aquarius Plus computer. Now you may ask, why do we want to make a bouncy ball fly around the screen on an Aquarius Plus computer? Well, it's kind of cool, and it's also kind of useful, because if you've seen some of my previous videos about the Aquarius Plus, you'll know that I think it's a really cool computer to begin with, and also it's a very good computer, I think, for beginners to learn programming on, particularly basic programming. And actually right now, the version of programming, or rather the version of BASIC that's being used on the Aquarius Plus, which is called Plus Basic, is currently under development. So it's even progressing and evolving as we speak, with all kinds of cool new features that make it really powerful. But I want to show you how I make an animation like this on the Aquarius, just using regular BASIC. I'm not using any sprites or fancy animation. This is just regular animation 101, showing you how I use this particular animation technique to make this ball bounce around the screen on the Aquarius Plus. And this technique can also be used probably for other character-based computers, and that's why this technique is so useful and easy to learn, because on an Aquarius or an Aquarius Plus computer, this technique can be used on both of those. They both use character-based graphics, which means that the positions on the screen correspond to memory locations. So whatever you put in that memory location, you put a certain value into a memory location, and then the corresponding image or character for that value will appear at that location on the screen. So if you're not already familiar with how the image works on the Aquarius computer or the Aquarius Plus computer, let me just bring over the manual and we'll take a quick look. Alright, so here is the manual for the Aquarius computer, the regular Aquarius computer, and I'll zoom in a bit. And you can see here that this represents an image of the screen, which is titled Character RAM Matrix. And the reason it's laid out this way is because these grids correspond to positions on the screen of the Aquarius. So you can see the top left position here, which is at row 0, column 0, corresponds to a memory location in Character RAM Matrix, which is the character RAM memory. That position corresponds to an address of 12328. But I should let you know that in the manual, it doesn't show you the hidden extra row that is actually at the top of the screen here. So there is another extra row that actually starts at address 12288, which is not shown on this diagram. So you can see here that the screen is laid out in a grid pattern, beginning with row 0, column 0 at the top left corner, and then these corresponding memory address locations simply increment by 1 as you go to the right. So this would start off at 12328, for example, then 12329, 12330, and then as you increase in rows, or you go down a row, then the address increases by 40. So you can see here, and I'll just zoom in even more. You can see here the address goes up by 40. So this top one is 12328, then 12368, then 12408, 12448, 12488. So you can see that every time you go one row down on the screen, the address increases by 40, and we're going to use that technique in our program today. But just remember that the top row is a hidden row, and it starts at address 12288, and we'll see that in a moment. So that is the character RAM matrix, and any value that you put into these memory locations will appear as the corresponding character on the screen. So how do you know what the corresponding character will be? Well, let's take a look at the character set for the Aquarius, which is right here. So you can see, for example, if you were to choose character number 25 here, if you put a value 25 into one of those character RAM memory locations, then this little robot symbol will appear at that corresponding location on the screen. And then just to complete our introduction to the Aquarius display, if we take a look up here, there is also something called a color RAM matrix. So these again are a group of memory addresses that correspond to screen locations. Only for these address locations, the values that you would put in there would correspond to the colors or the color attributes that would show up for that particular location on the screen. But for our program today, we're only going to be looking at the character RAM matrix, so we won't concern ourselves with the color RAM matrix for now. And I'll just move this back over. And so as you can see here, this is what we're going to produce, a little bouncing ball that ricochets off the walls and the floor and the ceiling of this image on the screen. So I'm going to show you how I do that and how I do the collision detection and changing the direction and all that. So the first thing we need to do is we need to generate the background image here, which has these walls. And the way I'm going to do that is I'm going to use a graphics design tool called Aquarius Draw, and I'll just bring that over now. But if you're not familiar with it, it's an online graphics development tool developed by Matt Pills. It's a fantastic tool, and you can just go to the link and access this tool, and I'll put that link in the description. So let me bring it over here. All right, so this is the Aquarius Draw tool. Makes it very easy for designing full screen graphics for the Aquarius and the Aquarius Plus computer. And you can see all the different characters you can choose are over here on the left. And this grid here represents the background image for the screen, or it represents the canvas for the screen. Now, keep in mind that the Aquarius Plus computer has extra features such as reprogrammable character sets, and it has sprites and all that. But like I said, we're not going to go into those fancy techniques today. We're just going to use some simple animation techniques. And like I said, the first thing we want to do is design our background screen image. Now, the technique I'm going to be using for making the ball bounce off of the walls and the floor and the ceiling is I'm going to use certain characters for the walls and the ceiling and the floor. And then my program is going to detect those characters. So then when the ball hits one of those characters, it will know that it's hit either the wall or the ceiling or the floor, and it will ricochet or bounce off accordingly. So first of all, let's choose a graphic for the walls. And I'm going to choose this graphic over here, which if you take a look and I hover over it, it's graphic number 214. So I'll just click on it, and you can see it gives me a black bar with blue sidewalls there. Well, I want to invert that. So to invert it in this Aquarius Draw program, I simply press F2, and there you can see it's inverted. And now if I click anywhere on the screen on this grid, it will place that character in that location for me. Now, one thing we should take a look at before we continue is remember that hidden row at the top of the screen I mentioned? Well, if you right click on the border up here, you can see there's options for disabling row 0. So right now I have that hidden row enabled. You can see it up here on the top of the screen. And if I click this disable row 0 option, then you can see that row has disappeared now, and there's one fewer rows on the screen. But I do want it enabled because I'm going to use it. So I'm going to right click on the border again and click enable row 0, just like that. So now I have that hidden row enabled at the top of the screen as well. So now let me finish drawing my wall character here, and I'm just going to draw it down the left and right sides of the screen, just like this. And I'm using the same character for both the left and right sides. And I know I can't see what I'm designing behind my head here, but I'll make sure the image is correct before we use it in our program. So there we have our left and right wall of the screen. And the reason we're able to use the same character for both the left and the right wall is that we don't really care which wall the ball is hitting, whether it's the left wall or the right wall, because the effect is going to be the same, which is to change its direction horizontally. And we'll get into that obviously when we take a look at the program. So now let's go ahead and design the floor and the ceiling. So I'm going to use a similar character for that, which is basically this same character but turned sideways. And that is pre-programmed in the built-in character set over here. And by the way, in case you're not familiar with Aquarius Draw, if you right-click on anywhere on these character set, you can see there are two options here. One is called Sorted Layout, and one is called Original Layout. Well, the way we're looking at it right now, this is the sorted layout. And by sorted, they mean it's organized in a kind of logical way so that similar graphics are grouped together. You can see all these ball fragment symbols are grouped together. These kind of step lines are grouped together. All these man symbols are grouped together. And the characters are grouped together. And these arrows are grouped together. So you can see it's organized in a kind of a logical way. But if we right click on it, and then we select Original Layout, then it sorts it in order of character value. And you can see the values if I hover over these characters. So here I'm hovering over the top left character up here, and you can see that there's a 0 that pops out. That means that character has a value of 0. and as you go along to the right, the numbers for the values just increase. So character 1, character 2, character 3, all the way to the bottom right here, which is character 255. So in case you're looking for a particular value character, that's how you can easily find it, by putting it into that layout. But I'm going to change it back to the sorted layout, which organizes everything kind of logically, just because it makes it easier for me to find different characters on the screen. So now let's see what character I want to use for the floor and the ceiling. Well, I'm going to pick this one right here, character 172, which looks like this. And again, I don't need to invert this one because it looks the way I want it to look. But if I wanted to invert it, I could just by pressing F2, and you can see it inverts it on and off. So I want it to look like this with the top and bottom black bars. And I'm just going to click on the floor here to fill that in. And the same for the ceiling. And again, the reason we're able to use the same character before the floor and the ceiling is because it's going to have the same effect. When the ball hits either the floor or the ceiling, it's going to change its vertical direction. So if it was going down, it's going to go up. If it was going up, then it's going to go down once it hits either the floor or the ceiling. So then, now what's left? Well, you can see we have these corner positions still not filled in. And we want those positions to have unique characters from the walls and the ceilings, because when the ball hits the corner, it's going to need to change both its horizontal and vertical direction. And for this one, I'm going to change it to the original layout, like this, and I'm going to choose character 255 down here, which is just a solid square. And this one, I don't want it to be blue, I want it to be black. And just in case you're not familiar with what these colors, where these colors come from, and what inverting does, if you take a look at the top of the screen here, you can see there's two rows of colors. The top row is the ink, and the bottom row is the paper. So right now you can see that the ink color we have selected is this cyan color, and the paper color is black. And you can choose whatever colors you want for these images, for these characters. So you could have, let's say, a red ink on yellow paper, or whatever you want. It won't matter for my program because I'm not detecting the colors, I'm only detecting the character. Although you could use the technique that we're going to be looking at in today's program to detect colors instead of characters if you want. And that would be handy, for example, if you had two of the same character, but they're different colors and you want to be able to detect them uniquely. So, but today I'm just going to use black and cyan, the default colors here. So let's say I choose black ink on cyan paper. Now I've got my black square here. And again, if I press F2, that will invert things. So now that's cyan ink on black paper, but I want it to be black. So I'm just going to press F2 again. Now I've got my black square again, and I'm going to put those in the corners. So here I'll put it in the bottom left corner, and the top right corner, and then the bottom right corner and behind my head here. And now the top left corner, you may be familiar with the unique properties of that location, which is any character and color you put into that location. This is the hidden top row, remember, we're using now. So any character and color you put into that location for the top left corner of the hidden row will also fill the border. So now you'll see when I put this black square in this location, then the border also gets filled with black squares. So it's not just filling it with the color, but it's also filling it with the character. So for example, if I chose maybe this heart symbol here, and maybe I'll make it red on yellow, just for demonstration purposes. If I put that character in the top left corner, then the border becomes filled with red hearts on a yellow background. But that's not what I want. I'm going to go back to my solid square character with a black ink on cyan paper, and there we go. So there we have our background image that we're going to use in our program. So now how do we save this image? Well, there's two ways that we save it. One is if you go over here to the file name entry, you can type in your file name, and I'll call this file Bouncy because we're making a bouncy ball. Okay, so there I've typed in the word Bouncy, and this image is going to be titled Bouncy when I save it. So let's see if I can move myself over here. Okay, there. So now let me first of all finish drawing this image. I'll put this black square down here, And now over here you can see there's a Save Scene selection. So I'm going to click Save Scene, and that will save a file called bouncy.json in my downloads folder. And that's the default file format that this program saves. But I also want to save it as a format that the emulator can open, or the actual Aquarius computer can open. So today I'm going to be using an emulator, but it doesn't matter. You can do this on real hardware or on the emulator. And I want to save it as an SCR file type. And luckily in this program there's an easy way to do that. All I have to do is press Control M, and I'll show you a little trick here. If you're not familiar again with this program, if you press F1, it brings up a really cool help feature here that shows you all of the hotkeys and key combinations that this program uses. So if we take a look down here at Control M, it says export screen memory. And so that's what I want to do. I want to export the screen memory, and what that's going to do is save the screen as bouncy.scr, which stands for screen. So I'll go ahead and do that now and press Control M. All right, so now I should have both a bouncy.json file, which I'm not going to use, and a bouncy.scr file. So let's go ahead and take a look at my Explorer now in Windows. I have two files, bouncy.json and bouncy.scr. So bouncy.scr is the file that I'm going to be using in my program. You want to copy this file here, bouncy.scr, either into the folder for the SD card in the emulator or onto the actual SD card that you're putting in your Aquarius Plus computer. Or if you're using a regular Aquarius computer, in order to load screen images like this, you're going to need a device such as the Aquarius MX or the micro expander, but of course you could just use the emulator like I'm going to be using today. So I'll go ahead and copy this bouncy.scr file into my emulator SD card folder. And I'll move my head back here. Okay, so now my folder should contain the screen image that we need, and it's time to start making our program. Okay, so here I am back in the emulator, and in case you're not familiar with the emulator, if you haven't used the Aquarius Plus emulator before, then I'll just give you a quick introduction to it and where you can download it, and I'll put a link to it in the description for the video, so you can go ahead and download it if you want, and I'll just show you what that looks like once you go there. Alright, here is the page for downloading the emulator, and since I'm using a Windows machine, then I download this file here, Aquarius Plus emu Windows x64 portable v0.8a.zip, or whatever version it happens to be at the time that you look for it. So this is the file. I just simply download this and unzip it wherever I want. Right here, this is my folder, and yours may look a little different because I have some other files in here, but you can see here there's an SD card folder which contains the files that would normally be on an SD card that you put into the Aquarius Plus, and that's where you want to put your program. And then this is just a backup I made of it, SD card back, so you won't have that in your folder. And then you can see here there's an Aquarius ROM. So for example, when Basic gets updated or Plus Basic gets updated, then you can download a new version of this Aquarius ROM file if you want and update your Basic version. Here's the file right here, aquarius-emu.exe, that you would click on to open the emulator. And then this folder here, SD card, is the folder where I'm going to be putting both my program and that screen image that we just created. And I've already done that, so I'll move this window back here, and let's go back to our emulator. Right here. So a couple things I want to show you about the emulator before we get started. One is, with both the emulator and the actual Aquarius Plus computer, it has a cool feature called turbo mode, which doubles the speed at which the emulator and the computer operates. So instead of operating at 3.5 megahertz, it operates at 7 megahertz, which is really cool. So right now my bouncy ball is bouncing at 3.5 megahertz, but if I press Control F, there you can see it's going twice as fast, and it's really bouncing along there. So this turbo mode is a really cool feature that will really help make your basic programs even more playable. And to slow it back down, I'm just going to press Control D. And you can also activate these turbo modes in your program as well. But I'm just doing it from the keyboard for now. And let's take a look at a couple other features that might be useful for us. So one feature you're going to need to know about is if you go up here to the System menu at the top left here, you want to tell the emulator where your SD card folder is. So right here at the top it says select SD card directory, and so if you just click on that, then you can go and choose where your SD card folder is. It's probably in your emulator directory, but you can set it to whatever you want. And so this is how you tell the emulator where your SD card folder is. And of course your SD card folder is going to contain both your programs and your screen images. So we're going to be using this folder in our program today. And so you don't need to be too worried about all the features of the emulator for now. All you need to do really is download it and install it and tell it where the SD card folder is. And we've already saved our background screen image into that folder. So now let's go ahead and create the program to make our bouncy ball bounce. So I'll just stop this by pressing Control C, and then I'm going to press CLS, which means clear screen. And then if I list the program, this gives you kind of a preview of the program we're going to be creating, but we're going to do it from scratch. So I'll type new to erase this program, then clear screen again, and here we are ready to start our program from scratch. All right, so what's the first thing we want to do? Well, in BASIC, the first thing we normally do would put the title of our program. So I'll just type line 10, rem, and I'm working in caps lock mode, and I'll call it Bouncy Ball by SpriteWorks. All right, and then the first thing we normally do in a program is initialize the variables. So I'll do that by calling a subroutine. So I'll say 100 go sub, and now here I'm going to put the line number for the subroutine where I'm going to initialize my variables. But here we have an interesting feature of the Aquarius Plus computer, which we didn't have on the regular Aquarius, which is with Plus Basic, we can now call subroutines using labels instead of line numbers. So in this case, I'm going to just precede my label with an underscore. That tells the computer that we're using a label, and I'm going to call my label var init for variable initialization. So now my program is going to go sub a subroutine called var init instead of having to use a line number, which is really cool. Like I said, these features are being developed in real time as we speak. So if you want to make suggestions as to what features you'd like to see, you better head over and join the Aquarius Plus Facebook groups and developer groups and conversation groups, and you can put in your 2 cents. So next I want to go ahead and make our variable initialization subroutine. And maybe I'll do that at line 5000, just like this. And again, I'll put my label here, var init. So this is where my variable initialization subroutine is going to be, line 5000, and it's identified with the label underscore var init. And there's another little trick I like to do when I create subroutines, which is I like to put a stop statement just before it. So for example, here at line 4999, I'll put a stop instruction just like that. So what that does is just kind of a fail-safe in case I really screw up my program and it accidentally tries to run into my subroutine by accident. So without calling it purposefully, sometimes the program might not be working properly, and just to prevent it from accidentally running straight through into my subroutine, I've got my stop statement there. You don't have to put that in, it's just a little trick that I use. But if you want to use that trick, you're welcome to use it. So let's say I clear screen again now, and we'll take a listing to see what we have so far. So we have our rem statement, we have a go sub instruction, which is calling variable initialization subroutine, which is down here at line 5000, variable initialization or var init. So now we need to go ahead and initialize our variables. So luckily this program doesn't use very many variables. It only has a few. But what type of variables do you think we would need for this simple bouncy ball program? Well, the first variable I'm going to assign is a variable that keeps track of where the ball is positioned on the screen. And like I mentioned, since the Aquarius Plus computer and the Aquarius computer uses character graphics that correspond to those screen locations and memory locations, we're just going to use those memory locations. And so let's choose a variable first. Let's say we'll choose a variable called BP. So I'll say line 5010 BP, and that's going to stand for ball position. But for this program, I'm going to actually need two ball positions. So the first ball position is going to be where the ball is actually located currently, and then the second ball position is going to be the potential ball position where it's planning to travel to. So that may be a valid position like an open space, or it may be an invalid position like a wall. So I'm going to need two variables to handle this, and I'm going to use an array for that. So it's very simple. I'm just going to use the first one, BP1, and that's going to be our current ball position. So equals, and so this, since I'm initializing it, is going to be the starting position for our ball. So where do we want our ball to begin? Well, let's take a look at our Aquarius Draw screen. Again, for this, our Aquarius Draw tool right here. And you can see, if you take a look at the top right corner here, and it won't show it while my cursor is there, but just keep your eyes on this top right corner here, and I'm going to hover over some different positions on the screen, and it's going to show you the corresponding memory locations or memory addresses that correspond to these locations. So let's say, for example, we want our ball to begin at a location around here somewhere. So, for example, if I just place a ball there now just for testing purposes, so this is where our initial ball will start in its travel on the screen. This is memory location 12990, as you can see up here in the top right corner. When I hover, you see it says 12990. So if you just hover over any screen location here, it'll tell you the corresponding memory address. And this one is 12990. So that's the one I'll use in my program. So back in our program here, I'll say BP1 equals 12990, and I'll put a rem statement, rem current ball position, just like that. And now we need another variable to keep track of where the ball is planning to go, because it's moving, right? So it's going to be calculated in the program where the ball is going to be positioned next. So I'm going to use a different variable for that, and that's going to be BP2. So I'll just say 5020 BP2 equals. So obviously, since we're initializing the variables, the program is not automatically calculating which direction the ball is moving and where it's going to be going next. So I'm just going to, for now, set the next ball position to equal the current ball position. So I'll set that to BP1, just like that. It doesn't really matter actually what value we choose here, because the program is going to be calculating it on the fly as it runs. But for here, I'm just going to put a rem statement to say potential ball position, just like that. Okay, so now we only need two more variables, well, for this initialization part of the program anyway. And so two variables that we need to keep track of are which direction the ball is traveling, both the horizontal direction and the vertical direction. So first I'm going to set up the horizontal direction by saying 5030, and I'll just use a variable called HD. And keep in mind, on the Aquarius computer, the computer only recognizes the first two characters of any variable name. So you can make your variable names longer than 2 characters as long as they start with a letter. So for example, you could use a variable called A, or A1, or HD, or you could have a variable called ABCDE. But just keep in mind that variables will only look at the first 2 characters of that variable name, and variables also can't contain any reserved words. Like, let's say print. You can't have a variable called print, for example, or have the word print in the variable name. So I'm just going to keep it simple and use 2 character variable names, and this HD will represent the horizontal direction for the ball. And remember when we took a look at the screen grid earlier, and we saw that the memory locations increment by 1 as they go to the right. And since my ball will initially start off going to the right, then I'll set my HD, or horizontal direction variable, as 1. HD equals 1, just like that. And I'll say rem horizontal ball direction, just like that. Then of course we need the vertical direction, so I'll put that at line 5040. VD will be my vertical direction. What value do we want for our vertical direction? Well, let's say I want the ball to start going up the screen, and remember the row numbers increment as they start from the top of the screen and go down. So since I want my ball to go up the screen, that means the row numbers need to decrement. So I'm going to give this a value of -1. Rem vertical ball direction. just like that. And then that is all the variables we need to initialize for now. So I'll just put another line number here, 5999, return. So it will return back from our variable initialization subroutine. Okay, so here's our program so far. We've just initialized the variables, but now let's go ahead and make up the rest of our program. So what's the first thing we want to do? Well, probably we'll want to display that image on the screen, that background image that we just created. So let's go ahead and do that first. So we initialized our variables here at line 100, right? So let's start our program at line 1000. And this is where we're going to load our screen image. So I'll just type rem load screen image. And then maybe line 1001. We're going to actually load the image, and we do that using a load instruction. And there are even more simpler ways to do this that are being developed now in Plus Basic, but for now we'll do it the regular old-fashioned way. And we'll say load, and remember our screen image, we saved it as the file name bouncy.scr, just like that. So load bouncy.scr, but then we need to tell the computer where in memory to load this image to, and we want to load it to the character memory, which begins at address 12288, which is the top left position in that hidden row. So we just say load bouncy.scr, comma 12288, and that should load our image for us. And do we want to test it out? Why not? So let's just run this program now and see what happens. And there you go. We have our background image loaded here. We have our walls and our ceiling and our floor. And then we have our break at 4999, because remember I put that fail-safe stop instruction in at line 4999 right here, 4999 stop. And so I'm just going to type CLS again to clear the screen and also change the border back to cyan. And let's list our program. And so now we've loaded our background screen image. And so what's the next we want to do? Well, the next thing we want to do is actually print the ball on the screen. But I'm going to do a little trick here, which is before we print the ball at the new location, even though we haven't calculated any locations yet, we've only initialized the first location. As our program runs, we're going to want to erase the ball at the old location and then print the new ball at the new location, right? So let's start off by just erasing the ball at the old location. Even though we haven't printed a ball yet, we know as our program runs, it will be printing the ball. So let's start off with our ball erase instruction. So let's do that maybe at line 2010, rem erase old ball, and then line say 2020, we're going to actually erase the ball. And how we're going to erase the ball is we're going to print a character at the old ball location. So let's go back to our Aquarius Draw tool right here, and I'm going to sort this by original layout so it's in numerical order. And then I want to look for a space character because I'm just going to print a blank space over the old ball. And so right up here you can see there's a blank space, and it has a code of 32. So that is the value I want to put into the character memory to represent this blank space, code 32. So if I click on it, you can see down here it shows me just a cyan background, so there's nothing printed there, just the paper color, which is cyan, is showing here, and that's exactly what I want. So I'm going to use that code 32 in my program to erase the ball at the current location. And remember, we have our variables here, BP1 and BP2, to represent the current ball location and the new ball location, or the potential ball location. So the current ball location is at BP1. So what I'm going to do is poke that memory address with the value 32, which represents a blank space. So I'll do that with a poke statement, of course. Poke BP1, comma 32. And you probably already know putting a colon in the middle of a basic instruction line allows you to add more instructions to the same line. So after this colon, I'm putting a rem statement like I've been doing before. So I'll say rem erase old ball, which is exactly what our other rem statement above it says we're going to be doing. So this is what this instruction is going to do, erase old ball. And I'll press enter. And so now probably you can guess we want to print the new ball in the new location. So how are we going to do that? Well, let's give ourselves some extra room here. Let's start this at line 2100. And what do we want to do? We'll say rem print new ball, just like that. And then maybe line 2101 is where we're going to actually print the new ball. And how do we print the ball? Well, we're going to do it again by poking a value into character RAM memory. So we're going to again use a poke statement. And where are we going to poke it into? Well, we're going to poke it into the new ball position, which you can probably guess is right here, BP2, potential ball position. And so we're going to use that variable, BP2 equals. So what value is the ball going to be? Well, again, we'll go back to our Aquarius Draw tool right here. And if we take a look at this ball that we've already drawn on the screen, and you can choose whatever character you want, of course, but if, let's say, I want to use that ball, and I hover over it here on the character display, you can see it has a code of 150. So that's the value that I'll use in my program. But of course, you could pick any character you want. I'm just going to use this one that looks like a ball, which has a code of 150. So back in our program here, I've already got my poke statement started, poke BP2. Oh, I don't need an equal sign there, do I? Poke BP2, comma, 150. And I'll say rem print new ball, which I don't really actually need to put these rem statements twice. It's kind of overkill, but it doesn't hurt anyway to do that. So far we've initialized our variables. We've erased the ball at the old location. We've printed the ball at the new location. So now what we want to do is we want to make the current ball position equal the new potential ball position. So we've printed the ball at the new location, but now we want to make that new location the current location. So let's do that at line 2200, and we'll say rem set current ball position. And 2201, we just want to make our current ball variable, which is BP1, remember? And we're going to make that equal BP2. And so now we're going to set our current position to equal the new position, or the new potential position, because since we've printed the ball at the new location, then we know that that's a valid location. We're going to set that as our current ball location, and then we're going to calculate a new location as the ball moves along. And that's what we're going to do right now. So let's go to line 2300, rem calculate new ball position. And let's say 2301. How are we going to calculate the new ball position? Well, of course, we're going to use those direction variables that we set up already. So remember, the variable that we're using for our new ball position is BP2. So we'll get started here and we'll say BP2 equals. Well, it's going to equal some offset from the current ball position, right? So we're going to say equals BP1 plus something or other. So what is it going to add to the current ball position to figure out where the new ball position would be? Well, it's just going to use those variables that we set up here, horizontal direction and vertical direction. So let's start off with the horizontal direction. And remember when we took a look at the grid for the screen positions, when you go to the right one position, the address increments by 1. When you go to the left one position, the address decrements by 1. So going left and right horizontally increments and decrements a value by 1. So that's what I'm going to use here, is since we already have our horizontal direction set to 1, I'm just going to use that variable HD. So the current ball position, and you add to that the horizontal direction. So it's either going to be +1 or -1, depending on whether the ball is going to the right or to the left. But what about the vertical direction now? So we're going to say plus VD, and our VD, remember, goes up and down the screen for vertical direction. But remember, the addresses go up and down by 40 as you increment and decrement lines on the screen. It's not by 1 anymore. So if you go up the screen 1 line, then the character addresses, or the character RAM location in memory, decreases by 40. So we need to multiply this variable by 40. And so remember, up here we initialized VD, or vertical direction, to -1, but we actually need that to say -40. So we're going to take that -1 and we're going to multiply it by 40. So I'll just put multiplied by 40 right here. So depending on whether the ball is going up or down, it's going to decrement or increment that character memory location by 40. So we'll press enter here. So now we've calculated our new ball position, but now we need to detect what's at that new position. Is it an empty space? Is it a wall? Is it a ceiling? Is it a corner? We need to know what is at that location, and this is how we do our collision detection. It's a kind of a neat trick, so we can, instead of having to use numerical values to calculate, is the ball in this position? Has the ball gone over this limit? We don't need to worry about actually calculating where the ball is, because we're using this trick to put characters there to detect when the ball is trying to move into a position that contains anything other than an empty space. So in order to do that, we need to detect what character is at the new location that the ball is trying to go to. So we'll do that at line 2400, and we'll call that get character at new ball position. And the way we get the character is simply by peeking the address where the ball is trying to go. So at line 2401, we'll say, now we're going to use another variable. This variable didn't need to be initialized because we don't use it initially in the program until it gets to this point. And I'm going to call this variable char for character. And you can see I'm using more than 2 characters in my variable name. That's okay because I know I'm not reusing these first 2 characters C and H for any other variable name. I could just use the variable CH if I wanted to, because the computer is going to ignore this AR anyway, but I'm just going to use char to make it readable in my program. So I'll say char equals peek, because I want to peek inside the memory location where the ball is trying to go to. And where is it trying to go to? Well, it's trying to go to this location here that we just calculated, BP2, right? So I'll say peek, open bracket, BP2, close bracket, just like that. So now we know what character is in the position where the ball is trying to get to, and we've saved that in this variable called char. And so now what we need to do is simply analyze this value of char and see where the ball is trying to go. And the way we're going to do this is we're going to set up 3 subroutines. We're going to check for 3 conditions. We're going to check if it hits either one of the side walls. We're going to check if it hits either the top or the bottom wall, or the floor or the ceiling, or we're going to check if it hits a corner. And so let's set up those 3 checks right now. We'll say line 2500, rem detect floor / ceiling. Okay, and I'm just going to set up these checks right now for readability so we know what we're doing. So we'll go to line 2600, rem detect sidewall, and then line 2700, rem detect corner. So those are the only 3 things we need to check. Does the ball hit the floor or ceiling? Does it hit the sidewall? Or does it hit the corner? So now let's put those actual check statements in the program. Let's say line 2501, which is going to check for the floor or ceiling. But first we need to know what character is the floor or ceiling, right? So again, we're going to go back to our Aquarius Draw tool here. And an easy way to check what character we're interested in is if you hover over the character and you look at the top left corner here, so just keep your eye up there, and then I'm going to hover over this character here, which is the ceiling. You can see the character is 172. And similarly, if I go back down to the floor and I hover over the floor position here, you can see again the character is 172. So that's why I use the same character for both the floor and the ceiling. And now we'll go back to our program here, and we'll simply use an if statement. If char, remember that's a character where the ball is trying to go, if the character at that location equals 172, meaning a floor or ceiling, then go sub, and it's going to go sub a subroutine that's going to do something. And so this is going to go sub a subroutine that represents a vertical collision, so it hits the floor or the ceiling. So I'm just going to call this one using, again, a label, which is a great feature of the Aquarius Plus. So I'm just going to title all my subroutines with the word sub. So I'll say go sub sub 1, just like that. And then line 2602 is going to detect a horizontal collision or a sidewall collision. Again, if char equals, and what's the code for the sidewall? Well, we'll go back to our fantastic Aquarius Draw tool, and if we hover over it, you can see the code is 214. So if char equals 214, then go sub 2. So then at line 27, Oh, I guess I've used both 2501 and 2602. It doesn't really matter. I'll just use 2701 again. If char equals, and now I want that corner position character. So let's go back to our Aquarius Draw right here. And if I hover over the corner character, you can see it says character 255. So that's the code that we'll use in our program. So if char equals 255, then go sub underscore sub 3. All right, now let's clear the screen. Let me just list lines from 2500 on to make it more clear. So there we go, line 2500, rem detect floor ceiling. So if it detects character 172, which is the floor and the ceiling, then it goes to sub 1. If it detects character 214, which is the wall, it goes sub 2. Then if it detects character 255, which is the corner, it's going to go sub 3. So now, of course, we're going to need 3 corresponding subroutines. So let's put those here at line 3000, underline sub 1, and 3100 will be underscore sub 2. Line 3200 will be underscore sub 3, just like that. Well, actually, let's do that again and make them a bit more descriptive. So if I go line 3000 underscore sub 1, this is detecting the floor or the ceiling, so I'll say colon rem vertical collision. And then line 3100 is underscore sub 2, and I'll say colon rem. This is detecting the side walls, so I'll say horizontal collision. And then finally the third subroutine, which is at line 3200 underscore sub 3 colon rem, and this is detecting a corner collision, just like that. So now if I go ahead and clear the screen and I'll list 3000, you can see there we have our 3 subroutines ready to go to detect if the ball hits either the floor or ceiling, which is a vertical collision, the sidewall, which is a horizontal collision, or the corner, which is essentially both a horizontal and a vertical collision. Okay, so now what do we want to have happen in each of these 3 subroutines? Well, we know the ball has collided with something, right? Either a wall or the ceiling or the floor or a corner. So the first thing we know is we don't want to print the ball in the new location because we're going to be printing it on top of a wall or something, right? Which we don't want. So the first thing we're going to do in each of these 3 subroutines is to reset the ball position back to its current position. And we simply do that by adjusting the BP2 variable to set it back to equal to the original BP1 variable. And so I'll go ahead and do that in each of these 3 subroutines. I'll start with line 3010 in the first subroutine, and I'll say BP2 equals BP1, and I'll put a colon and then a rem statement, reset ball position. Then same thing for the second subroutine at line 3100. I'll say line 3110, and I'll just type the same exact thing, BP2 equal BP1 rem reset ball position. And similarly for line 3210, BP2 equals BP1 rem reset ball position. Not terribly efficient, but it gets the job done. Okay, so let's just list our program again here from line 3000 and see how it looks now. All right, so now in each of these 3 subroutines here, sub 1, sub 2, and sub 3, we're resetting the new ball position, BP2, back to its original ball position, BP1, because we don't want to print the ball in the new position. All right, so now what else do we want to do in these subroutines? Well, since the ball has hit something, that means its direction is going to change, right? So if it was moving up and it hits the ceiling, then it's going to rebound and move down. If it hits the left wall, it's going to rebound and move right. If it hits the corner, then both of its direction variables are going to be reversed or inversed. So let's take these one by one. And we'll start with sub 1 here, which says vertical collision. So if the ball hits either the floor or the ceiling, then what we want to do is reverse the vertical direction. And so I'll do that at line 3020. And remember, the variable that keeps track of our vertical direction is VD. And so we're going to set it to something. So we'll say VD equals what? Well, if we want to invert that variable or change it from a positive to a negative or negative to a positive, then all we need to do is simply put a minus sign in front of it and repeat that variable, VD. So VD equals minus VD. So if VD is 1, meaning the ball is going down, then we set it to -1 and the ball starts going up. Very simple. And I'll say rem reverse vertical direction. And we're going to do something similar for each of these subroutines. So in our second subroutine here, at line 3100, sub 2, horizontal collision. So now the ball has hit one of the side walls. So here we'll say at line 3120, we need to adjust our horizontal direction variable, which is HD, and we're going to do exactly the same thing, equals minus HD. Rem reverse, oh, I misspelled that first one, that's okay. Reverse horizontal direction, just like that. And then in our final subroutine, the wall has hit a corner, so we need to reverse both the horizontal and the vertical directions, because if the ball was, let's say, traveling to the top left corner, that means it was moving up and to the left. Then we need it to rebound exactly opposite, and now it's going to move down and to the right. So we need to reverse both the horizontal and the vertical direction variables. And to do that, I think you can guess how we're going to do it. We're going to exactly copy these two lines of code. So we'll start here at line 3220, and we'll say VD equals minus VD, reverse vertical direction, and then at line 3230, HD equals minus HD. Oops, I forgot my rem statement up there. Okay, I better fix that. 3220, VD equals minus VD, rem, reverse vertical direction, and then 3230, HD equals minus HD, rem, reverse horizontal direction, just like that. Okay, so now let's clear this again and clear screen, CLS, and we'll list the program here and see how it looks. Oh, looks like I forgot a rem statement here at line 2400. It just says get character at new ball position. Well, that's not going to work. So let me just fix that. Control C. So 2400 rem get character at new ball position. Okay. And now we'll clear the screen, list it. Okay, that looks all right. So now what else do we need to do in these three subroutines where the ball has collided with the wall or the ceiling or the corner or something? Well, this might be a good place to do some ball animations. For example, you might want to flatten one side of the ball as it hits the wall and see what that looks like. Or you might want to maybe play some sounds. You could easily put in some sound statements here. So if I clear the screen again and I list these subroutines from line 3000, and I'll stop it there. So here is our first subroutine, sub 1, and we've gone up to line 3020. Well, what if we put in 3030? We could put a sound statement like this, and maybe we'll play sound 10 100, right? So you could put in sounds if you want whenever the ball hits the wall, and you don't want to make the sound very long because it's going to slow down the program whenever the ball hits the wall. But you could put in a short sound like this, and you could just put a statement rem sound, and you can do that for all of the subroutines if you like. So let's say 3130 sound 10 100 rem sound, and then line 32 40, sound 10, 100. And if you wanted, you could play different sounds depending on which wall it hits. Rem sound. And okay, good. So there we have sounds now. And now, of course, since these are subroutines, we need to return from each of these subroutines. So I'll put in my return statements here. I'll start with line 3099, return, to return from the first one. 3199, return. 3299, return. Okay, and there we go. And let's test it out. Let's run it and see what happens. So I'll clear the screen and I'll type run. All right, and let's see how it looks. Return without go sub error in 3099. Okay, so it's run into subroutine at line 3000 and hit the return statement without go subbing. So this is why I put those failsafe stop statements in. And let's put one in at line 2999, just before that subroutine at line 3000. So if we take a look at our subroutines here, they start at line 3000. So I'm just going to put in a stop statement at line 2999. 2999 stop, just like that, just in case the program tries to accidentally run into our subroutines without calling them properly, which is what happened here. And the reason that happened is because we never put in a go-to instruction to loop back to the beginning of our main program loop. So we need to do that. Well, let's take a look at our listing here. So you can see here that our listing goes up to line 2701, where it detects the final corner character. But then after that, we need to loop back to the beginning. So where is the beginning of our program where we want to have our main program loop? Well, let's take a look here. So line 1000 loads the screen image. So we don't want to reload the background screen every time the ball moves, right? So line 1001 load bouncy.scr, we don't want that in our main program loop. Line 2010 rem erase old ball. So when we start erasing the old ball and printing the new ball, obviously that is part of our program loop. So it looks like our main program loop starts here just before line 2010. So let's make it start at line 2000. And so I'll type line 2000 rem main program loop. And then let's use a label to identify where our loop begins. So maybe at line 2001, I'll put underscore, and then I'll call this main program loop start. So we're going to loop back to the start. And then we need a go-to statement to come back to this start instruction before the program runs into our subroutines at the end. So if we do a listing here, we can see that right here at line 2999 we have our failsafe stop instruction. So we want to put our go-to instruction to loop back to the beginning somewhere before this. So why don't we put it at line 2800. So I'll say 2800 go to start. Just like that. So now let's run it and see what happens. There we go. Can you hear the ball bouncing? I'll turn up the volume a bit. There we go, success. So now we have our bouncy ball subroutine working. And I'll just turn down the volume here. But before I do that, you can see this is running in the original 3.5 megahertz. So I'll go ahead and press Control F on my emulator keyboard here. And now you can see it's running a lot faster. It's running at 7 megahertz now. So that's a really handy feature to have in this Aquarius Plus computer or Aquarius Plus emulator. And it really speeds up your basic programs and makes them a lot more playable. So I'll press Control D to slow that back down. And like I said, you can activate this feature in the actual program if you want. You don't have to press a key on the keyboard to activate this turbo mode. You can activate it from within your program. Oh, it looks like there's a slight glitch with the graphics here. My image is lost its black border. I'll press Control C to stop, and I'll run it again, see if it fixes that. Okay, so it looks like there's a slight bug in my program where it's printing blank spaces where the ball hits the corner. So let's take another peek at the program and see why it's erasing the ball at the old location, or rather it's printing the ball in the corner. It shouldn't be changing the ball location when it hits a corner. So let's find out why. And it's most likely going to be in one of those subroutines that starts at line 3000. And it should be the last subroutine, which is right here, sub 3, rem corner collision. And I can see the problem right here. It says BP1 equals BP1. Well, that's obviously not correct. It should be BP2 equals BP1, so it sets the new ball position, which is BP2, to equal the current ball position, BP1. So let's go ahead and fix that now at line 3210. BP2 equals BP1. And I wonder if any of you caught that while I was actually typing it in. I'd be impressed if you did. Not surprised, but I'd be impressed. Okay, so BP2 equals BP1, rem reset ball position. All right, now this should work. And there, so it hit the corner up here, and it didn't change it to a space. So as you can guess, this is probably, well, I know it is, a very easy program to convert into a breakout style program or even a Pong style program. It would be very easy to convert this into your own game and make it an actual playable game, either a one-player game or even a two-player game. And if you find this kind of programming interesting, then you can imagine what kind of possibilities there are for programming games for the Aquarius Plus computer now that it has new expanded and enhanced capabilities such as sprites and tile maps and this new cool turbo mode. So there we go. We have our Bouncy Ball program working on the Aquarius Plus emulator. If you want to check it out for yourself, go ahead and download the emulator, join the Aquarius Plus groups if you like, and play around with it and do some programming, and hopefully you'll get inspired to make some of your own games and come and share them with the group. So thanks for watching, and we'll see you next time.